Hello and welcome to our lesson on triangles and solving. So before we get into the solving and the fun stuff, a couple things we should know about triangles up to this point. First, if we have a triangle that contains a right angle, we should know that that is called a right triangle. So triangles containing right angles are called right triangles. And now the next one, I'm not sure that we've talked about this one, but hopefully we know what a triangle is called when it does not contain a right angle. So if a triangle does not contain a right angle, we call it an oblique triangle, and that may be new. I'm not sure when's the last time you took a geometry class, but oblique triangles are usually they're broken into two categories, so maybe that name is avoided because we have more specific names. In your oblique triangle, so your triangle that does not contain a right angle, you may have all acute angles, in which case that oblique triangle is called an acute triangle. Or it may be the case that you have one obtuse angle, in which case the oblique triangle would be called an obtuse triangle. So hopefully those sound familiar because they are forms of oblique triangles. Sometimes we avoid calling triangles that name, but it's the case that if it has a right angle, it's a right triangle. If it does not, it's an oblique triangle. And again, those oblique triangles are either acute, so they have three acute angles, or they are obtuse, which means they have one obtuse angle and two acute angles. And we should also know, way back from the beginning, that the three angles in any triangle add up to 180 degrees. Now, what we're going to be doing a lot of in this module is solving triangles. And we're going to talk more about that in a minute, but we have to understand that every triangle has 6 unique fundamental properties. So every triangle is unique in that it has 3 distinct side lengths and it has 3 distinct angles. So every triangle has 6 unique and fundamental properties. Again, those would be its 3 sides and its 3 angles. Now, even though every triangle has these 6 fundamental properties, in general, knowing only 3 of the 6 fundamental properties is going to be enough to guarantee the remaining properties. So what do I mean when I say that? Well, there are some theorems, 5 of them to be exact, that given 3 properties to create a triangle, all created triangles would end up being congruent. And if triangles are congruent, it's like congruent's the geometric word for equal. It means that all 6 of the fundamental properties in those 2 triangles would be equal or have the same measure. And so what I'm trying to say is, for example, in this first one, we have a triangle congruence theorem called side-side-side, the SSS, side-side-side, triangle congruence theorem, which basically says that even though 2 triangles have these 6 fundamental properties that make them unique, if I gave every student in my class 3 specific side lengths, so I said, here's 3 like popsicle sticks, and one's 3 inches long, and one's 4 inches long, and one is 5 inches long. If I gave the same 3 measurements to every student in my class, every student would create the exact same triangle. All the triangles created in class would be exactly the same. Even though I'm not mentioning what the angles are, those 3 side lengths guarantee that the angle measurements would have to be the same. So we have the side-side-side congruence theorem that guarantees if 3 sides of a triangle are congruent to 3 sides of another triangle, then those 2 triangles would be congruent. So not only would their sides be equal, their angles would be equal as well. We have a second theorem. It's called the angle-angle-side theorem, AAS, which means if we have in that order an angle, angle, and a side, that means we have 2 angles and a side that is not included. These 3 components, these 3 properties would be enough to guarantee that any 2 triangles with that angle, angle, and not included side congruent would have to be congruent. So when we say angle, angle, side, again, we're meaning 2 angles and a side that is not included. So if you look at the picture, here is an angle that's labeled here, here is an angle that's labeled here. The included side would be the side that is included in those 2 angles. It would be right between those 2 angles. If the side is not included, it could be over here or it could be over here. So this side is not included, this side is not included. So think about reading this. You have an angle, and the side, you have an angle, then a side, you have an angle, and then you have a side. So when I'm reading this information that's given in this picture, I have an angle, and then a side that is not in between those two angles. So, oops, I meant for my eraser to go on. If that's the case, if I have two congruent sides, or two congruent angles and a side not included that's congruent, and they're corresponding, again, that's going to be enough information to guarantee that any two triangles with those properties will be the same. Okay, we have another. It's called, trying to scroll here to my next one, the angle-side-angle congruence theorem. So again, even though we have 6 properties for this triangle or for any triangle, if I have two angles congruent and the included side, so this time it's angle, side, angle. The side is right in between those two angles, and that's what we see in the picture. Here's an angle, and here's the side that's right in between those. If I have those 3 components that are the same in two triangles, those two triangles have to be the same. So just knowing those 3 components would guarantee that this side length has to be what it is. It would guarantee that this side length has to be what it is, and it would guarantee that this angle has to be what it is. Okay. The next one we're going to look at is called the side-angle-side theorem, and the order that we're labeling these things is important. So this time we have 2 congruent sides and we have an angle right in between those two, so that's going to be called the included angle. So you have a side, and then you have an angle right in between those two sides. So if we have the same thing in another triangle, we have the same side that we have here, we have the same side that we have here, and we have the included angle here, the same in both, that even though we only know those 3 components, the others are guaranteed. So this side is guaranteed to be the same length as this side, this angle is guaranteed to be the same measure as this angle, and this angle is guaranteed to be the same measure as this angle. So knowing just a side and an angle and a side guarantees the remaining components of the triangle. Okay, I'm scribbling all over this. And the final one is the right angle hypotenuse side theorem. Sometimes this is called RHS for right angle hypotenuse and then a side length or a leg. Sometimes it's also called HL, so hypotenuse leg, and a hypotenuse only applies in a right triangle, so it's sort of implying that there's a 90 degree in there. So this is saying if we have a right angle, which means we have a right triangle, and we know its hypotenuse, so again I have a right angle, and we know its hypotenuse, so right angle, we know its hypotenuse is congruent in both, and then either one of the legs, but it's corresponding, so I have a leg here congruent to a leg here. Knowing those 3 components guarantees these triangles have to be congruent. It guarantees that this remaining leg would have to be congruent. It guarantees that this acute angle would have to be congruent to this acute angle, and it guarantees that this acute angle would have to be congruent to this acute angle. So just knowing that I have a 90 degree angle, a congruent hypotenuse, and a congruent leg guarantees that the rest of the components would have to be the same. Okay, I'm making a mess of my picture here. Now the last thing I want to show you is commonly mistaken for congruence theorem, but it is not. Side angle, right? We did all this combinations of sides and angles up here. Another combination side angle does not work. We do not have a congruence theorem that says if we have 2 sides and an angle that's not included, that the 2 triangles have to be congruent. That's not going to be sufficient for congruence because 2 triangles could actually be created. So for example, and I put 2 pictures in here, but really this is the one I want to show you. If you have a side, let's say your side length is 6, you have another side, let's say in this case it's 11, and then you have an angle that's not included. So this would be the included angle. A not included angle would be like this angle over here. Then you're not guaranteed to make the same triangle. There are 2 different triangles that could be created. So if I took this, it's kind of hard to show it here, but if I took this leg, the length of 6, I could stretch it out so that it, let me show you this part first. So if I have, again, the side length here of 6, the side length here of 11, and then I have this 30 degree angle. Well, the other leg of the triangle that I would have to make here, let's just say I made it with a dotted line because I don't know where it's going to go yet. The 30 degree angle guarantees that that's the angle that it's going to have to go on, but this side length of 6 here, where is it going to intersect? It could intersect here, or it could intersect here. So because if you were to just take the endpoint here and just swing it around, you see how it makes this arc? Like these are the two places where it could intersect that third side of the triangle. So because we have an option of the side length being there, or we have an option of the side length being there, again, this wouldn't be enough information for us to guarantee the congruency of these two triangles. So we have side, 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 angle, side, angle, 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 side, angle, side, and then HL or RHS. That's kind of called two different things there, but this is not a triangle congruence theorem. And we're going to see it come back in when we talk about something called the law of sines and how we have this ambiguous case because there are different things that could happen. But for now, let's see what we could do knowing the information from the 5 actual congruence theorems that we do have. Okay, what we can do is basically solve a triangle. So what does it mean to solve a triangle? If we're solving a triangle, it means we're finding all 6 of its fundamental properties. So we're going to be given 3 of those properties, the 3 that would satisfy one of our congruence theorems. Based on those 3, the other 3 have to be guaranteed, and we should have enough skills eventually to find those 3. So for example, in number 1, we're going to be solving a right triangle ABC given, well, first it's a right triangle, so you know one of the angles, and a side length here and a side length here. So based on just those 3 components, we should be able to find the other 2 angles in the triangle as well as the third side of the triangle. So we're going to be given 3 components. We're going to find the missing 3. Right now we have enough skills to do this with right triangles, and then after we look at what we call the law of sines and the law of cosines, we'll be able to do this for any triangle. Now, for consistency in labeling and solving, we need to make sure that we're all on the same page. So what we're going to do is we're going to let a, lowercase a, represent the side that is opposite of angle A. We're going to let lowercase b represent the side opposite of angle B. And then lowercase c is going to represent the side that's opposite of angle C. So we're going to use capital A, B, and C for angles, and then lowercase a, b, and c for the sides that are opposite of those respective angles. So again, here's angle A. If I go opposite of angle A, I have side A. And then here's angle B. If I go opposite of angle B, I have side B. And then here's angle C. If I go opposite of angle C, I have side C. And in a right triangle, A and B don't matter. Now I put an oblique triangle in the picture, but in a right triangle, A and B, remember those legs are interchangeable, but C is always our longest side, and so C would always be our, capital C would always be our 90-degree angle. Alright, so let's try this out. We're going to try to solve right triangle ABC. And let me first sketch this out. And I have a nice little sketch tool that's going to make my triangle perfect. I bet you're wishing you had that. Okay, so here's my right triangle. A, B, and C. First I want to label my angles. I want to label the sides that I'm given and figure out exactly how I'm going to solve for what's missing and what's missing. So C is our hypotenuse in our right triangle. I'm going to go to put 53.58 centimeters here. And again, this is going to be angle C. And then the other 2 are interchangeable, so maybe I just call this one A and I just call this one B. So across from angle A is lowercase a. That's our side length given to us is 29.43 centimeters. And that's all I'm given. Okay, I'm given triangle ABC. I labeled all those angles. I labeled the side opposite of A and the side opposite of C. So based on this information, we should be able to solve this triangle. That means we got to find the missing angle here, we got to find the missing angle here, and we have to find the missing side here. So I don't know what's jumping out to you, but I think the first thing I would do is find the missing side, which is lowercase b, because the Pythagorean theorem can be used to find the missing side of a right triangle, right? So let's do it. Let's find that missing side b. So b squared plus a squared, which is 29.43 in this case, has to equal the hypotenuse squared, so 53.58 squared. And then basically going to have to go to the calculator. I'm going to leave this in this squared format for a second. I know I'm going to subtract that 29.43. Oops, I forgot my square. So I have 53.58 squared. I'm going to subtract over the 29.43 squared, and then ultimately have to square root that. I just don't want to input too many things into the calculator if I don't have to. So I'm going to go one final step into the calculator here would be the square root of 53.58 squared minus 29.43 squared. That way I don't have to worry about, again, let's square this and then subtract and then take the square root. It's just a lot to input. So we're going to save ourselves a little bit of that work. So I'm going to put in one expression, square root of 53.58 squared minus 29.43 squared. And so b is going to be not equals. It's going to be approximately equal to, let's be precise here and make sure that's not an exact equal. This is going to be about 44.77. I think rounding to the hundredths place is sufficient. And that's going to be in centimeters. Okay, so I was given two of the sides. Now I have the third side. So now I'm one step closer to this triangle being solved. Now I also need to figure out the measure for angle A, and I need to find the measure for angle B. Let's say I wanted to find the measure for angle A. I have lots of options for this, but what I want to do when I'm finding angle, or what I don't want to do when I'm finding angle A, is use side B because I've already approximated that. So I want to use the given sides as much as possible to avoid rounding multiple times within one problem. So if I was going to solve for angle A, then I would probably use the side that is opposite and the side that's the hypotenuse here, not side B because I've already rounded that one. So if I have the opposite side and the hypotenuse, the side that is opposite of that angle and the hypotenuse of this triangle, then I can use the sine to solve for A. I can say that the sine of angle A that I'm looking for, which will be in degrees, right? We have a 90-degree triangle already, or angle already in there. The sine of angle A is going to be equal to a ratio of that opposite side, 29.43, over the hypotenuse, 53.58. Now we just did a whole bunch of solving like this in our previous module. We were looking for an angle on the unit circle that gave us a ratio. Obviously this is not a ratio that's going to be on the unit circle, so we would use the inverse sign. So I take the inverse sign on this side. I take the inverse sign on this side. These are inverse operations. They will undo one another. And so my angle A is going to be equal to, in the calculator, I'll put in the inverse sign of my 29.43 over 53.58, and it will give me an approximation for angle A. And again, make sure that you're in, I'm already in degrees, but make sure you're in degrees. So if I want the inverse sign of my fraction, 29.43 over 53.58, then I have it. And it should make sense. This is an acute angle. The two angles in your right triangle, other than the two angles outside of the right angle, right, have to be acute angles because together they're going to make 90 degrees. So this is going to be about 33.32 degrees. So now I'm almost done. This triangle, again, is going to have 6 components, but I was given 3, had to solve for 3. I've solved for 2 of those. Right now I have 2 of my angles. I have all 3 of my sides. I just need to find that last angle. Now to find the last angle, I could do exactly the same thing I did with A. I could pick another color here. Say that, alright, here's angle B that I'm looking for. This is the adjacent side in the hypotenuse, and I could use the cosine to find that angle. But also remember that the 3 angles in a triangle have to add up to 180 degrees, and so knowing 2 of them, I can just subtract from 180 to find the third. So that's what I'm going to do here. If I add up angles A, B, and C, they have to make 180. So angle A, which is 33.32 degrees, plus 90 degrees, plus the missing angle B, all those together have to make 180. So angle B is going to be 180 minus the 90 and minus the 33.32 that I already have in there. So all together, I'm going to end up with a calculator. So I have 180 minus the 90 and minus the 33.32, so 56.68 degrees. And this is also going to be an approximation because this is an approximation. So this was, no, I forgot my answer. 56.68. And we've done it. Okay, we have solved, and I don't want that to be there. Sorry, I'm just going to move this because I don't want it to be squished in. Okay, so B, approximately, one more time, 56.68 degrees. And we did it. We solved this triangle. Okay, so again, knowing 3 of the properties guarantees what the other 3 have to be based on those triangle congruence theorems. So this allows us to find the 3 missing components given the 3. And I guess I should have mentioned this in the beginning, but why are we guaranteed this particular triangle? So think about the information that we were given. We were given the right angle, we were given the hypotenuse, and we were given one of the sides. So technically, this triangle is guaranteed. That means the missing pieces that I found there are guaranteed to be what they are by that RHS theorem. Okay, so that's, again, important to keep in mind because there's going to be cases that aren't guaranteed where we see that side-side angle, not enough information to guarantee there. So there's that ambiguity of 2 different possible cases. So we'll have to be really careful when we get to our next section. All right, so let's try this one more time. We're going to be solving a right triangle ABC if angle A is 34 degrees 30 minutes and C is 12.7 centimeters. So again, let me just label this first. Let me draw out my right triangle. This is an important part of the process. Remember, C is our longest side. That's our hypotenuse. So I'm going to go ahead and put my 12.7 centimeters here, which means this has to be angle C across from it. And then A and B don't matter, so I'm just going to call this one A and I'm going to call this one B. And I know that angle A is 34 degrees 30 minutes. So I'm going to put my 34, can't really fit that in there. So I'm going to just say in there is 34 degrees and 31 minutes. So I have 3 pieces of information. I have an angle here, it's a right angle, and then I have the hypotenuse, but I don't have another side. Okay, what I have is an angle, and then I have another angle, and then I have a side. So this one is guaranteed not by RHS. Every time it's a right triangle doesn't mean it's a right RHS guarantee. This is by an angle, and then a side that is not included in those 2 angles. So this is guaranteed by the angle-side congruence theorem. Okay, so that theorem says that no matter what, right, if I gave you those 2 angles and that side that's not included, that any triangle I could create with those properties would have to be the same as this triangle that's here. So that allows me to solve for those missing pieces. So now let's do that. Let's solve for those missing pieces. I think the angle would be the easiest one to find here first, the missing angle B, because again the 3 angles in the triangle have to add up to 180 degrees. So angle B, just like we did a few minutes ago, if I take 180 degrees and subtract out the 90 degree angle and subtract out the 34 degree 31 minute angle, then I'll have left the measurement of angle B. So for angle B, let's do a little mathing here. I have 180, subtract out the 90, and let's subtract out the 34, so ignore the minutes for just a minute. We end up with 56 degrees. So 180 and 90 and 34, or 180 minus 90 and 34 left me 56 degrees, but I still have to subtract from that the 31 minutes. Now remember, those are 31 minutes are out of the 60 minutes in each of our degrees. So I'm going to have to borrow from the 56. So I'm going to call this 56, instead of 56 degrees, I'm going to call it 55 degrees and 60 minutes, and then I can subtract those 31 minutes. So left over for B is going to be 55 degrees and 60 minus 31 is going to leave me 29 minutes. So now I have my angle B. Now I have all three of the angles. I was given the 90, I was given angle A, now I have angle B. Now I need to find the other sides. So again, I want to, as much as possible, avoid rounding, but I don't actually have anything rounded yet. So even though I solved for B, that's an exact measurement. So I can use any of the information I have to try to find my missing sides. So let's say I wanted to find side A, which would again be opposite of angle A. What information do I have access to? Well, lots of information, but let's say I wanted to use the, I don't know, it really doesn't matter. I'm just trying to go back and forth. Let's say I use angle A. Okay, side A is opposite, so this would be the opposite side, and I know the hypotenuse. So I would use the sine if I wanted to use angle A. Maybe for variety I don't do that. If I wanted to solve for A, I could also use angle B, in which case this would be the adjacent side and the hypotenuse, and then I could use cosine to solve. So it doesn't matter. You can use either one. I just wanted to show you the options, but since I have it here with cosine, let me take that route. So the cosine for angle B, which we know is 55 degrees 29 minutes, has to be equal to a ratio of the adjacent side, A, over the hypotenuse, which is 12.7. So if I wanted to solve for A in this one, I have to get rid of division by 12.7, which means I'd have to multiply it over. So A is going to be equal to 12.7 multiplied by the cosine of 55 degrees and 29 minutes. Now, if you remember in Desmos, we don't have a minutes key. So if I want to put that into my calculator, I'm going to have to put in 12.7 and then multiply it by the cosine of 55 degrees plus, remember that 29 minutes is 29 out of 60 minutes in each degree. So I divide it by 60 to convert it to degrees. So if I put that into my calculator, then I should get the approximation for A. So I want 12.7 multiplied by the cosine of 55 degrees plus 29 sixtieths of a degree. And again, make sure I'm in degrees, and I am. Okay, so that means A is going to be about 7.196. That'd be about 7.2 if I was trying to round to the hundredths place, and this would be centimeters. Okay, so now I have side length A. And now I just have one last piece. That's to figure out the measure of side length B. Now I know I have two sides of my triangle. I have the option of using the Pythagorean theorem, but if I wanted to use Pythagorean theorem, I would have to include one of these measurements which I have rounded, and so I don't want to do that if I don't have to. So I want to stick to using the given exact measurements as often as possible. So now I have the same options for finding side length B that I had for finding side length A. I can use angle A on the hypotenuse, or I can use angle B on the hypotenuse, and then depending on which one's which sine or cosine. So maybe I use angle A this time. If I'm using angle A, this would be the adjacent side, and again this is still going to be the hypotenuse. And so I could say that the cosine for angle A, which was 34 degrees 31 minutes, is equal to a ratio of the adjacent side, which is side B, over the hypotenuse, which is 12.7. So B is going to be basically doing the same thing, right? We've got to get rid of that division by 12.7, so we multiply. So B is going to be exactly equal to 12.7 multiplied by the cosine of 34 degrees 31 minutes, but I can't put that into my calculator, so it's 12.7 times the cosine of 34 degrees and 31 sixtieths of a degree. And now I can get my approximation. So I'm just going to go in here and cheat because I already typed this in. Change this to a 34, and then change this to a... You would do this too. It's not really cheating. It's work smarter, not harder. So 12.7 multiplied by the cosine of 34 and 31/60ths of a minute means our side length B is about 10.46 centimeters, and we're done. Okay, so we were given three components of this triangle, guaranteed by angle, angle, side. We were able to solve for the missing three components, and now this triangle is solved. All six of its fundamental unique properties are known. Okay, so one last little note I want to make here, which is something I talked about, but I forgot to put it in a blank somewhere, right? We want to round as little as possible, so avoid using rounded values in continued calculations. Okay, so we want to use exact values as often as possible. Avoid using rounded or approximated values in calculations, like in further calculations, right? Obviously, you're going to get a rounded value for these answers. You just don't want to use them again. Calculations. Sometimes talking and writing at the same time doesn't compute. Okay, so we did it. Nice little recap. Hopefully nothing earth-shattering here. We've solved for missing sides and angles in right triangles before, but what we're going to be doing as we move forward is applying this same process of solving a triangle to oblique triangles. So solving in a right triangle is something that isn't really new. Solving in an oblique triangle will be new. We will have to guarantee our given information. Do we have angle, angle, side, angle, side, angle, side, side, side? Or do we have one of those congruence theorems that guarantees what the missing components of our triangle are going to be? And based on the guarantee and what we're given, we're going to learn something called the law of sines and then the law of cosines to be able to solve in the same way. So not just solving right triangles, but being able to solve oblique triangles is where we're headed. Alright, so I think you have enough to work on your practice for this time, but as always, if you have any questions, reach out. Until next time, take care.